Hello everybody. In this video we're gonna solve one problem just to demonstrate how to use the equations and how we can use the information that we were discussing before about calculating the mass transfer coefficient as part of a big problem. And this is a very important point because sometimes we don't focus on the application, especially in this kind of topics, because we focus more on the equations. So here we will cover this problem where we have a spherical drop of liquid water, which is this. It has the diameter of 1.5 millimeters originally, and it falls in quiet dry air. And we mean by quiet dry air that the air is dry, which means that it's not or does not contain any humidity. So the partial pressure of water in air is zero. Quite that there is no turbulence, so the motion is only due to the falling of the drop. So there are no other forces acting on the drop other than the gravitational force, and we will know why this is important. And as it falls, due to the difference in humidity, or the difference in partial pressure of water between the surface of the drop and the air outside, water will evaporate. So the volume will decrease with time. So it starts here with diameter 1.5, and after some time of falling, it will reach another diameter, which is of course less. And this diameter or this volume here is 50% of the original volume. And we assume that the velocity of the drop is its terminal velocity evaluated at its mean diameter. So there is something that in fluid mechanics that's called the terminal velocity of a falling particle, and this is the velocity of a falling particle that falls, or its motion is due to the gravitational force. The velocity will be dependent on the acceleration due to gravity, of course, and the difference in density between this material and the fluid outside it, so or around it. So yani, for instance, if you put or drop like a rock in water, it's going to be different from dropping it in a more dense fluid. So the difference in density is going to make a difference. So this is what we call the terminal velocity, and of course this includes also some friction force due to the viscosity of the fluid and other things. So anyway, so this is what we call the terminal velocity, which we say here. And this terminal velocity is function of the size of the falling particle, or the diameter of this particle. So we will assume that since we have two diameters here, d1 and d2, so we will assume that this velocity is calculated at the average velocity, which is the average the average diameter between d1 and d2. The water temperature is 293 Kelvin, which is this, and the air temperature is 323 degrees Kelvin. And the equation that we use to calculate the terminal velocity of a falling particle is this. It's a very, very famous equation. It's function of the particle diameter, the density of water, density of air, the acceleration due to gravity, the density of air, and the coefficient of drag, or drag coefficient. And we will see how to get this coefficient. But this is the parameter that takes into account the friction with the surrounding fluid. So we need to know how much distance L that this drop needs to fall from, starting with a diameter of 1.5 millimeter until it reaches the diameter that will lead to 50% reduction in volume. So to do this, we need first to have a plan of solving this problem, and based on this plan, we will arrange the solution procedure. So simply to get this distance, we know that we can calculate the velocity. So if I can calculate the terminal velocity using the given equation, and if I know the falling time, then I can know the distance. So I know how much distance it goes per unit time. Then if I know how much time it will fall, then I will calculate the traveling distance. As we said, the terminal velocity is calculated from this equation. We will go through this equation in details. This is should be easy to get. The next step is to calculate the falling time, and this is the mass transfer part here. So the falling time is going to be the time that the drop takes from or while it's losing its mass, or losing mass due to mass transfer from D1 to D2, or its volume decreases from D1 to D2. So the falling time is going to be the amount of water evaporated divided by the rate of mass transfer in gram moles per second. So if you know how much water evaporated and you know what is the rate of mass transfer, I can from both I can get the time that will take this amount of water to evaporate using this given rate of mass transfer. The amount of water evaporated is very easy to get. You can get it from the difference in volume and the density, so it's not a big deal. The rate of mass transfer is going to be the mass transfer part, which is the area multiplied by the flux, and the flux is K multiplied by C minus C infinity. So this is what I should be thinking of while solving this problem. So what I need to do is first to calculate the average or the terminal velocity. I need to calculate the amount of water evaporated, which is not big deal, to the rate of mass transfer, which is not difficult, by the way. The only thing here is that I don't know Kc, Cas, and C infinity are easy to get. The area of mass transfer is very easy. So Kc is the point that we uh, and the terminal velocity, by the way, these are the 2 points that will take a little bit of time, and this terminal or the rate of mass transfer is the step that will be mass transfer related through all these steps. But it's important to have this plan in your mind, just to know what is your next step, where you are going, and how this will help you to reach your goal. So first, this is what we mentioned last time, that we have two different temperatures and we want to get the film temperature. And just to be aware of this, we have water which is pure water, so there is no gradient in the water phase, which means that there is no driving force, so there is no mass transfer in the liquid phase because the concentration is the same everywhere. So mass transfer is gonna take place only in the gas phase. So the film temperature is going to be the average between the liquid temperature and the gas temperature, which is 308 Kelvin, and all the physical properties that we are going to get in order to calculate the mass transfer coefficient are the properties of gas phase, the water in the gas phase, not the liquid phase. So or the properties of the gas phase, and we will need the water just to get the density of water for the amount evaporated. So just to make it simple for us, we will go for the properties one by one. So first we will get the properties of water at 293, which is the temperature of water. We need the density of water. As you remember, here we said in this slide that we have here the density of liquid water. This is liquid water, it's not vapor. This is liquid water because this is the water I started with, the amount of water I started with, and the amount of water I ended up with. So this is the amount of or the density of water. I can get it simply from the tables. There are tables in the appendix, one of the appendices in the end of the textbook, where you can find the properties of different liquids. This is liquid water. You'd see that the temperature is 293. It's already given. That's 998.2 kilogram per meter cube. For the air, we will get the average or the properties at the average film temperature, which is the density and the viscosity of air. Let's see here that I have 308 here, I have 300, 320, so it's going to be something in between these two values. So I will get the value by interpolation, by linear interpolation, to get the density of air and the viscosity of air. So now I got the physical properties. I need to get also the diameter, the new diameter. So the new diameter, I can simply get it by equating the new volume as 50% of the old volume, and substitute by the volume as pi over 6 d power 3 for both sides, and then I can get d2, and for this I can get the average diameter, which is the d1 plus d2 over 2. Finally, I need to get the diffusion coefficient of water in air, which is given. I can find it in the tables in the appendix in the textbook, but I have it at for water in air at 298 Kelvin. So I will multiply it by the factor T over T power 3 over 2 to get the diffusion coefficient at the new temperature. Omega D will not make a big difference, so I didn't include it. So here we'll see this is the diffusion coefficient. So here I got all the information that I need to start solving the problem. So first I'll start with the first step, which is the calculation of the terminal velocity. Again, I want to remind you that these are the steps I'm following. So I'm here in this step, which is calculating the terminal velocity. So the equation that we have to calculate the terminal velocity of a falling particle is this. We can substitute with the information that we have, and then the equation would be a function of CD power 0.5, and then I need to get the value of a CD in order to get the terminal velocity. But the CD is not straightforward parameter that you can get. The CD, there are equations that you can use, or you can use this chart to get CD based on Reynolds number. So you have it for different shapes. For this sphere, this is the curve for the sphere. This is in the fluid mechanics part of the textbook, so it's not in the solution in the textbook, so I put it here just to know how we can get the terminal velocity. So based on the value of Reynolds number, we can get CD. But here we will have a kind of dilemma here. So I need to know Reynolds number in order to get CD, and I need to get CD in order to calculate V node, and V node is what I use to calculate Reynolds number actually. So I'm going in a circle here. I need every one of them to get the other. So this is going to be solved by trial and error. You have to assume something and then recheck on it. So to do this, we have to calculate Reynolds number. So Reynolds number is rho multiplied by V node multiplied by D over mu, and this is why we said that this is the air is still air or stagnant air, because the motion of the drop is only driven by the gravitational force or the terminal velocity. So this is Reynolds number. You substitute with the information that we have. Of course, there are all the information of air, and then we have Reynolds number. We can combine both equations in order to get Reynolds number as function of CD directly. So I have Reynolds number as a function of CD, and I have here CD as a function of Reynolds number. So this is going to be easier than going through 3 equations. I'm going only to use 2 equations. So this is going to be a trial and error process, so or an iterative solution. So I will do many trials. So I first assume CD as 1, and if you put CD as 1, then Reynolds number is 320. If you go here, of course, this is not going to be very accurate because you don't have clear cuts of the numbers here. There are very big differences that are not easy to get like an accurate result from here. So you might get different results if you try this yourself. They're not exactly the same as I get, but this is what we expect. So 320 should be somewhere here, and then if you do this, you will find that this is the new value of CD, which is around 0.6. And repeating this many times, you will get the value of CD as 0.55. By substituting, you can get the velocity as 5.27, and then Reynolds number, and you can calculate Schmidt number. So this is V node that we need to calculate, and this is Reynolds number. So if we go back here to the steps of the solution, I'm done with this. I got the terminal velocity, and now the next step is to calculate the rate of mass transfer, and I need to get Kc. So this is the point I am going to work on right now. So going back to the solution steps, we will see that I have already Reynolds number, I have Schmidt number, and I'll just plug the information I have in the proper equation that we use to calculate the terminal, the mass transfer coefficient. But again, we will go back to the equation. You'll see that in this, and you can check this in the PDF file where I put all the information or all the types of mass transfer equations for different shapes. You'll see here that this is this can be a natural convection mass transfer or forced convection mass transfer. So it's not clear is it I don't have anything to tell if it's natural or forced convection. So I have to do the check, and this check is to calculate Grashof number, and I calculated it, and it is 27,905, and to calculate 0.4 multiplied by Grashof per half, Schmidt power negative 1.6. You can check this in the PDF file just to make sure that this is the check that or these are the conditions that you have to that must be fulfilled in order to use the equation that we're going to use. So if you calculate Reynolds number, compare Reynolds number to 0.4 multiplied by this term, Reynolds is going to be larger. And by the way, this is one thing that I changed in the problem given information, that the textbook says that the initial diameter was 1 millimeter, but if you use 1 millimeter, then this condition is not satisfied. And the solution in the textbook didn't include any check on this condition. So I increased the diameter little bit in order to make this condition valid. So this, if this condition is valid, then natural convection is negligible and the effect of forced convection is dominant, and in this case you can calculate mass transfer coefficient using this equation. I know Reynolds number, I know Schmidt number, so I can calculate Sherwood number. Sherwood number, I know already Kc, dP, and I know the diffusion coefficient. So Kc can be calculated to be 0.262, and then I can calculate the rate of mass transfer using this equation. I know Kc, and let's go back to the slides, the solution steps. So I'm done with calculating the mass transfer coefficient. I need to get the driving force and the cross-sectional area and the amount of water evaporated, and then plug everything in the equations and we're done. So the difficult part is already done here. So the CAS is the concentration of water as the gas interface, which is the concentration corresponding to the saturation pressure. So this is saturation pressure divided by RT, of course assuming that this is an ideal gas. And then we can get CAS as 0.94 gram mole per meter cube. So the rate of mass transfer can be calculated. Area is pi d square, of course, because it's an area of a sphere. And then the rate of mass transfer is given. Now I have the rate of mass transfer in gram moles per second. The amount evaporated that we can calculate is from the density, and the difference in volume is going to be in terms of mass. This is mass, not moles. So I have to get it in units of moles to unify the units of rate and the units of amount evaporated. And then and simply just divide this by the molecular weight of water, which is 18. So it's as simple as this. And finally, you can get the falling time from the amount evaporated and the rate of mass transfer. So this is the amount, this is the rate of mass transfer, and then you can get the time. And from the time I can go back to to here. I know the time, I know the terminal velocity, and I can calculate the distance that we need to, or this drop needs to travel in order to reach 50% of its original volume. So this is the final answer, which is going to be around 62 meters. So this is a good example for solving a problem using combining information from fluid mechanics and from mass transfer. And if you remember these problems in chapter 27, where we dealt with some of these problems, but we already had the mass transfer coefficient as a given value. And this is the new thing that's added here in this chapter, that we don't have the mass transfer coefficient as a given value, so we have to calculate it ourselves. So I hope this problem is clear now, and I'll see you the next time, John. Goodbye.